Good afternoon, guys. Today we will continue with what we started last week. And the idea here is to finally arrive at what we are used to, Ku equal to F. Yeah. Let's take the same problem, but little bit we will rephrase the problem, meaning that what we will do today is we will find this kind of expression for a given problem which is given like this. So this is a bar, and both the ends we have F1 here, we have F2 there, and which is given like this. See the direction of these two forces. Okay. Now, how to write that equation? Again, we will assume that A and E both are constant. Yeah. Accordingly, we have the equation which is we are now used to. We have seen since we started chapter 2, we know what it is. This will be equal to 0. Why? Because Bx equal to 0, there is no body force. Hence, we have this equation. We know the weak formulation of that, and weak formulation will be like this, will be WEA du dx L 0 minus 0 to L EA dw over dx times du over dx equal to 0. Yeah, this is what we have. Now we want to solve it, and how we want to solve it? Let us say this is U1, this is U2, and we want to write Ux in terms of U1 and U2. So we write Ni Ui, yeah, I equal to 1, 2, 2. So where we already know, we will write N1x equal to 1 minus x over L, N2x equal to x over L. So we know we have used the linear interpolation function. These are the shape function or interpolation functions, and we will use that. What we are doing today is just that we have put F1 here. We did not fix it here. Last time we fixed it here and we solve it. Right now we are not fixing it. We are saying it has U1, which is may not be equal to 0. And we have what we are given is F1 and F2, meaning that we have this strong form, and we have the boundary condition which is given. So boundary condition is of the strong form is this. Okay, so let's look at the boundary condition. What boundary condition we are giving? So we have bar here. At one end we have F2, another end we have F1. Both are in positive x direction. Now we know this one, right? We write, remember this is U is displacement. Then you have du over dx, which is a strain, right? Then you have E times du over dx, right? That will be a stress. Yeah. And then you have EA du over dx equal to force. But in which direction? Remember that we are multiplying with this force is nothing but sigma times A. So remember, sigma is important. Now, if you have some force which is applied this way, that means that tells you what? This is a kind of tensile. This is a tensile force which we applied, right? This is a tensile force. And hence, that should give positive strain or positive stress. Look at F1. F1 is compressive force, right? This is trying to compress it. Hence, this should give you negative strain, and that means negative stress. And accordingly, remember, we have to define the boundary condition. So boundary condition, this is straightforward. We know that we write EA. So look at the strain, right? The strain first, du over dx is positive here. Why? Because this is tensile. Because this is strain. Strain is positive because also this tight tensile force. This is how the convention is for this type of elasticity, right? So this is positive when when the strain is tensile, that is the force applied is tensile. So, and the force itself is tensile here. So we can write EA du over dx equal to F2. This is the boundary condition number 1. Now boundary condition number 2, what do we know? Here this is compressive, right? So whatever the force is, we have to write this in terms of a strain. In terms of a strain, this is compressive. So what we should get is some negative value, meaning that BC2 will be du over dx has to be negative. E is a positive number, A is a positive number, so whole thing has to be a negative number, and V should be a force basically, so which is equal to minus F1. F1 is absolute. The F1 is the magnitude of the force and which is being applied at x direction. However, when we write boundary condition, we have to write minus F1. Why? Because boundary condition, you are giving to the strain, although you are multiplying with EA, but actually you are giving the boundary condition to a strain only. This is the rate of change of displacement, that to that you are giving the boundary condition, and hence this has to be a negative number. Okay, any question, guys? Okay, now these two boundary conditions we will apply to this weak form. So what do we have? We have first, so weak formulation. We have WLEA du over dx at x equal to L minus W0 EA du over dx x equal to 0, right? And then we have minus 0 to L, right? 0 to L EA dw over dx, right? Du over dx equal to 0. Let's write here, instead of minus equal to 0, what we want to do is I want to say equal to this, no 0 here. Okay, so I will remove that. Okay, so let's write this equal to this. So this is left hand side, this is right hand side. Okay, so our left hand side is equal to what? We have this at x equal to L, we know that this is F2. So this is WL times F2. Right? And then you have minus, this is W0, right? And this one is what? This one is minus F1. So that makes it simply W naught, W at x equal to 0 times F1 plus W at L F2. Yeah, or let it be like that. Now what we want to do is we want to have a test function, and you want ux as a function of ni ui that I have written already, where I know what is n1, what is n2, right? So basically ux equal to n1x u1 plus n2x u2, right? And that means du over dx equal to dn1 over dx times u1 plus dn2 times dx times u2. Yeah, right? So this is what we have. So we write it as, simply you can write it as dn1 over dx dn2 over dx multiplied by u1 u2. This is what du over dx is. Similarly, we define w the same way, right? So the way we are defining weight function, also we can define the same way. Wx, maybe not there. So weight function w is equal to ni w wi I equal to 1 to 2, or wx we can write it as, or dw over dx, right? So anyway, wx will be equal to n1x w1 plus n2x w2, and that really means what? That means w, first of all we want to find out what is value of w0. w0 will be equal to w1 multiplied by n10 plus w2 n20. n10 is value is 1 is equal to w1, right? Either we know that when x equal to 0 this is w1, or you can also know by this n1 is equal to 1 when x equal to 0 and n2 equal to 0 at x equal to 0. So this becomes 0, and hence you have this. Similarly, wl is equal to w1 n1l plus w2 n2l. This becomes 0. n1l is 0 because n1 is like this and n2 is like this. Yeah, so I will just draw also. So this is how it is. This is n1 and this is n2, right? Okay, so is equal to w2, and similarly we have dw over dx equal to, also we will have dn1 over dx dn2 over dx multiplied by w1 w2. So we have from left hand side, what do we have? So far from left hand side we can write here, this is, we have this, right? So w0 is w1 multiplied by f1 w2 times f2. That is what the left hand side is. Yeah, so here we can write left hand side equal to we have w1 f1 plus w2 f2 is equal to let's go to next page. Left hand side is equal to w1 w2 multiplied by f1 f2, right? Now right hand side is equal to what? We have 0 to L EA du over dw over dx du over dx is equal to, right, 0 to L EA. Now what do you have? Du dw over dx, and we know that we wrote it like this: dn1 over dx, dn2 over dx, and then w1 w2, right? Then this is what it is, right? This one. Then you have du over dx, so again we multiply that with dn1 over dx, dn2 over dx multiplied by u1 u2, right? So this one is du over dx multiplied by dx, right? Okay, the same thing we can see, guys. This dw over this one, this we can also write it as this. So dw over dx can also be written as dw over dx can also be written as like this: w1 w2 and dn1 dx dn2 dx. What we are doing is, since it is a scalar number, right, dw dx is w1 multiplied by this, w2 multiplied by this. So this is a scalar number, so we can also, so either you write this way or you can transpose of it, which will be, this will come here and this goes here, right? You can write like this one. So instead of writing like this, let's write like this one. So then what happens? Look. Okay, so we have right hand side is equal to 0 to L EA. Then we will have W1, W2, right? And then dn1 dx, dn2 dx, and then you have dn1 dx, dn2 dx multiplied by, here you multiplied by u1 u2 dx, right? Okay, now w1 w2 is not a function of x. These are the constants, so these we can bring it out. Similarly, this guy is also constants, so we can also bring that outside. So this becomes equal to w1 w2 0 to L EA, right? And then you have dn1 over dx, dn2 over dx multiplied by dn1 over dx, dn2 over dx, right? Then dx. And then you have here, you multiplied by u1 u2, which is outside. Yeah, okay, let's call this one 0 to all EA, this. Yeah, let's call this thing as K matrix. So this becomes, we have W1, W2, we have a K matrix, and then you have U1, U2. So this whole thing is K. Okay, now go to left side. We have right hand side, left hand side as W1, W2, then F1, F2, and here you have W1, W2, K, U1, U2. So what do we have? So we right hand side equal to left hand side, and we have W1, W2, K, U1, U2 is equal to W1, W2, F1, F2. Now W1 and W2 are arbitrary. Yeah, so W1 is not equal to 0, W2 not equal to 0, and hence what we get? We get K times U equal to F, where U is U1, U2, and F is equal to F1, F2. We got this one. Only thing is now we have to see the details. What is K? U has the nodal displacement. U1 and U2 are the two nodes, U1 and 2. Whatever displacements are, they are here. F1, F2 are nodal forces. So whatever node number 1, you put force here. Node number 2, you put force here. That's it. Now K is something that we have to explore. K is equal to 0 to L EA. Okay, and then what do we have? We have here dn1 dx, dn2 dx, and dn1 over dx, dn2 dx, dx. This is K matrix. Okay, you also write in terms of, you call it, this is a B matrix. B matrix is dn1 over dx, dn2 over dx is B matrix. So K also you can write LEA, then B transpose B dx. You also write in terms of that. Yeah, this is a B matrix. You call it a B matrix. So B has the shape function, gradient of the shape function is there in B matrix. Yeah, either in this form, or you will see B matrix will take different forms. So, but this is what the K given by BK. Now this will be equal to K11, K12, K21, K22. And how will be, see here, this is 1 and 2, 1 and 2. Kij is given by simply 0 to L EA dni over dx, dnj over dx, dx. This is very powerful statement. This tells you that how these individual stiffness matrix components can be calculated. So this is 1, 2, 1, 2. So this is 1. Kij equal to EA dni dx over dnj over dx dx. For ij equal to 1, 2, right? Or maybe we write like I equal to 1 to 2, j equal to 1 to 2. Right? Now we can do the calculations, right? So let's do K12, K11 equal to 0 to LEA dn over dx. Now n1 is equal to 1 minus x over L. So that means dn1 over dx equal to minus 1 over L. N2 is equal to x over L. That tells you dn2 over dx equal to 1 over L. So similarly we write K11 is equal to dn1 over dx multiplied by dn1 over dx dx. Why? Because Kij is equal to I here, j here. I or j equal to 1 only. So hence both will be 1 only. So that becomes, now EA is constant. If E is a function of x, A is a function of x, then you have to integrate it here. But if it is constant, it can go out. So it can go out EA 0 to L, and then dn over dx is minus 1 over L square dx. So K11 is equal to EA, right? And then over L square multiplied by L is equal to EA over L, right? Similarly, you can find out all of them. Similarly, you can find out K22 equal to same thing, EA over L. Yeah, K12 you will find out is equal to K21 is equal to 0 to L EA, and dN1 which is minus 1 over L multiplied by dN2x, dN2 over dx, 1 over L. So 1 over L dx. You can find out this, you get minus EA over L. So basically what you get is big K is equal to EA over L, 1 minus 1 minus 1, 1. What is the final equation? Since Ku equal to F, final equation becomes EA over L, 1 minus 1 minus 1, 1. U1, U2 is equal to F1, F2. Yeah. So this is what we were looking for. In order to get it, we had to make a lot of background. We had to dig some background, how exactly it works. Finally, we connect it to chapter number 2. Yeah. So what we see is chapter 2 plus 3 plus chapter 2 is whatever we did. Same thing you can get if you study chapter 3, 4, 5. Yeah, all together. Chapter 3, 4, 5 all together when we study, then you get this one. Any question, guys, so far? Okay. Now let's look at the how assembly works, right? There we did assembly different, we did just assemble it, but here what exactly is going on? Now same kind of problem we have, let us say we have like this. We apply a force F1, we have a force F2, we have a force F3. We have applied a force, remember it. Yeah, so we have node number 1, node number 2, node number 3. Yeah, just demonstrate. I'm demonstrating that how it works. There is no body force. You can assume F2 as a body force, point force, a body force basically. But since we are defining a node there, so accordingly we have to look at it. Now you can tell that this is node element number 1, this element number 2. Okay, and you have force applied just between the two elements. You cut it here, then what do you get? If you cut it here, you will get like this. So let's call like this. You have F1, and then here let's call it F1, 2. So what is, you call it F12. Yeah. Okay. Yeah, it's fine. This is called F12, and this one on another half part, this one, it will also have some force there. So let's call it this one F21. Yeah. Or let's see the nomenclature. This one is, just hold on, we write differently. Yeah, so this is fine, I guess. Yeah, it was better. Yeah, so F1 means node 1, second node. no, sorry, we have element 1. Element number 2, node number 1. Node 1. Okay. So this is the force. This is the force at this is the force on element number 1 at node number 2. So node 1 and 2. This is local numbering, right? First node, second node. Here also first node, second node. Local numbering. Say local numbering. Say 1 and 2. So local node number. Similarly, this becomes 1 and 2. So local node number. Okay. Here we have this one. I should have written like this. So these are element number. So this is element number 1, element number 2. Yeah. Okay. Now, what we know here, this is F12 and F21. If you add them, what should you get? So F12 plus F21, you should get equal to F2. This comes from mechanics. If you cut somewhere, you get reaction, right? Let us say if you cut it here, what happens? Reaction force inside here and force inside here, they both should match and becomes 0. But when you have external force applied here, you cut exactly here, then what happens? Whatever the force, this one and this one, you should add up to F2, whatever is the final force, right? They should add to become whatever is the external force applied. So this is the equation you know. Yeah, remember that. Important to mention here so that we proceed with that. Now it's easy to see this F3. Now we will formulate now, right? So you have this problem, the element number 1, and we have F1 here. This we have F1, 2, right? And we have EA. Let us say both are constant. Then we know the equation for this, right? Which equation we know? We can derive it the same way, and we will find that the value will be EA, right? Then 1 minus 1 minus 1, 1. We will work the same way. And then you have U1, U2. So you have U1 and U2 is equal to, you have F1 and F12. Right? You got this. We have already derived this. We got exactly like this one. Yeah. Similarly, this is element number 1. Element number 2. You can do the same kind of this is F1. This is E over L. Okay. So your L could have been different, for example. So let's we assume both are different length. Yeah, we can assume it. This is L1 and this was L2. We can also assume. Right? Okay. So you have E over L1, or even you can assume for here to here E is different, L is different. You can also do that. Yeah. You can also assume that from here to here L1. Okay, why not do it? So from here to here we have E1 or A1. From here you have U2, A2. And length is L2 that we have mentioned. Right? So material property is different here and here. Then from 1 we get E1, A1, length is L1, E1, A1 over L1, this equal to this. We have F1 applied, sorry, this will be, for this one we will have F12, this is U2. The same U will also be there because both are same point. So if this moves by U2, this will also move by U2. So you have U2 here. Here you have F3. Okay, what is the equation we get? Now this is E2, A2, length is also L2. So we get E2, A2 over L2, 1 minus 1 minus 1, 1. U2, U3 is equal to sorry, this should be F21, guys. F21, yeah, F12 is here, this is F21. Okay, so this F21 and F3. Okay, so we have equation 1 here, this equation number 2 here. If you combine both this and this, combining 1 and 2, and what you get? You will get like this: EA over E1, A1 over L1, E1, L1 minus E1, A1 over L1, E1, A1 over L1 plus E2, A2 over L2 minus E2, A2 over L2 minus E2, A2 over L2, E2, A2 over L2. Yeah. Right. So we have 0 here, we have 0 here. Yeah. So combining this, we will have, let's write it, Ku equal to F, where K is given by this. Yeah. And U will be given as U1, U2, U3, and F will be given by F1, F12 plus F21 and F3. And we know that F12 plus F21 is equal to F2. Hence, it tells you that F is nothing but F1, F2, F3. Yeah, got it. If E1 equal to E2 equal to E, L1 equal to L2, A1 equal to A2 equal to A, then what we get? Ku equal to F means EA over L, 1 minus 1 minus 1, 2 minus 1 minus 1, 1, 0, 0, U1, U2, U3 is equal to F1, F2, F3. Right? And so on. So basically, we see automatically we are getting this kind of solution. And what we have assumed, if you look at the trial function, what we are doing, our trial function for the whole length, if x equal to 0, x equal to L1, x equal to L1 plus L2, and our trial function is something which is given here, goes like this, and it could be any value. what value? We have u1 here, we have u2 here, you have u3 here. Yeah, this is how it is. What is this? Sorry. We are making sure here that trial function is a piecewise. Trial function, what kind of trial function we used? We used, for this we used a linear between a linear trial function. For here also we took a linear. There is a continuity here, but there is a kink. Since we took the line linear, piecewise linear, piecewise linear. It is a piecewise linear. That really means that if you have a big problem, like this, and you have node number 1, 2, 3, 4, 5, and so on. And if you had force applied here, F1, F2, F3, F4, F5, and corresponding U's are U1, U2, U3, U4, and U5. Then accordingly, also we can write our U displacement vector will be equal to U1, U2, U3, U4, U5. Transpose of that force vector will be F1, F2, F3, F4, F5. Transpose of that. And how will we construct K? For K, we have to take individually, right? So this is the ith element. If this is the ith element, then this will be Fi, this will be not Fi, sorry, a small f, right? This will be Fi1, right? And this will be Fi2. Ith element, node number 1, this is the force, and like this one, this is the ith one, and then you have Ei, Ai, right? So the stiffness matrix of ith element, Ki, yeah, or let's write this eth element. This is typically used as eth element. So you have Ei1, Ef, E2, EEAE. So E is the element number. So KE means the stiffness matrix for the eth element is given by KE is equal to, you can do the same stuff, right? You can do N1, N2, or do all those things. So, and you can you do everything in local coordinate system, right? So you have x equal to 0, x equal to L1, LE, local coordinate system you can use, right? So the way we have done earlier, so KE you will get equal to LE 1 minus 1 minus 1 1, like that, and then you assemble it, right? Then you assemble, right? And then when you assemble, it will automatically you will get the big K. So K is assembled based on K, individual K's, right? But you know that mathematically how it fits. Mathematically it fits because we have shown, because of this automatically fits it. now in case of this solution that you get will be, so if you have x here and you have ux and you get solution which will be like this depending on, right? So your solutions will be like this. This will be u1, u2, u3, u4, u5, u6, u7, whatever value you will get like this. So you get the linear solution. Yeah, linear solution between two nodes. Yeah, but the actual solution, total solution is like this. Instead of having a line, a continuous line between the two nodes through the L, through the whole length, what you get is a piecewise line as a solution, which is known as finite element solution, right? So this is how it works. Any question, guys? Any question now?
Sir, yes, sir. Sir, as you said that our trial function should be piecewise continuous. So when the number of nodes are more, we have number of nodes, we have more number of nodes, then do we need to check the continuity, or is there any method of that, or we just consider it as we have done before, N1 U1 and N2 U2?
No, continuity already is made sure already, because at a node, see what happens. As a node, for both the elements, it has the same displacement. So automatically whatever the solution you get, make sure that this is continuous. You don't have to put extra effort. By design, it is like that, right? Got it? No? Yes or no, man? For this problem, let us say you had x equal to 0, x equal to L1, x equal to L1 plus L2, right? So that this is L1, this is L2. Your ux is given, how will you write? ux will be, let us say equality u1, u2, and this is u3. Whatever we did, that really means that ux equal to 1 minus x, right? 1 minus x over L1 multiplied by u1 plus x over L1 multiplied by u2 for x greater than 0 and less than L1, and is equal to 1 minus, 1 minus x minus L1 over L2 multiplied by u2 plus x minus L1 over L2 multiplied by u3 for x less than L2 greater than L1. So you are writing your ux now, or trial function is this, right? You put x equal to L1, this will give you u2, this will also give you u2. So this automatically makes sure that it is continuous to begin with, right? Yeah.
Okay.
Any other question? Is it difficult to understand, guys, or easy to understand? How do you find the course? Is it difficult to understand? Easy to understand?
Sir, I think the understanding is not the problem, but the things are new to us.
Okay. That's why I'm trying to make it that way. I'm not changing, not making it a steep actually. So I can understand this is a new course, of course. Most when you have a new course, then you have to take time to actually understand it. The best thing is to solve the problems. More you solve the problem, more you get out of it. Yeah. So if you solve all the exercise problems, you are good. Yeah. Look at the solutions, the problems which are solved in the book itself. So that way also you will understand. Okay. Okay. So here basically what we are trying to say that our trial function itself we are assuming to be piecewise lines basically. Yeah. And because of that you get the solution which will be piecewise line only. So in trial functions, what we did in the first one, we assumed that it is between u1 and u2, right? This is interpolated between u1 and u2. The second one between u2 and u3. Mathematically, you can write like this only. There's no other way, right? So this is how you assume the trial function to be. You solve it, you get the solution like that.
Hello, sir.
Okay. Yeah.
Sir, actually in homework 1, in one of the question, I got answer 27.2419 and the correct answer is...
Send me email, man. Okay, so we are not discussing the homework here. Okay, so you send me an email, it will be corrected. Okay, no problem.
Okay,
if there's a slight difference, then I send me email, then I will look into it. Okay.
Okay, sir.
Okay, guys. Also, you have a quiz number 1 scheduled on next Monday. That's on 14 February at this time at 2 p.m. Okay. So details I have posted on Google Classroom. Okay. So study, guys. Yeah. Okay. If there's no further question, see you on Wednesday in the tutorial class. Okay.
Hello, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Hello, sir. Am I audible?